In this video, we're going to learn a bit more about IP addresses and how they're split into a network and a host part. We're going to learn that networks can be divided into subnets and know how a subnet mask is used to identify the network part. So let's start. The Internet Protocol, IP, is an address which is a unique number, and we use it to identify a host computer or node which communicates over IP on the Internet. Now, there are currently two versions of IP in use today: IP version 4, which is the focus of this video, and IP version 6, which we're going to look at in a slightly later video. So here's a typical IP version 4 address. It's a series of numbers from 0 to 255, which behind the scenes are stored in 8 bits. So there's 32 bits in total, or 4 bytes, and we separate them by these decimal points. So this is an example of a typical IP address. Now let's dig behind the scenes in a bit more detail. So because we obviously have 32 bits, 32 ones and zeros, this gives us a range of around 4 billion possible IP addresses, from all the zeros and then all the combinations up to all the ones. Now it's slightly less than 4 billion because there are some special reserved IP addresses which we can't use, and you can see those down here. Now there are two parts to an IP4 address. There's the network identifier and there's the host identifier. And don't get too hung up on this diagram on remembering that the network identifier is the first 24 bits. That's just this example. This can change and you'll see that in a moment. But in this example, the first 24 bits are being used to identify what network the PC is on, and the last 8 bits are being used to identify which actual PC within that network the IP address belongs to. And you can see here we can add the /24 on the end to represent this. Now I'm just going to mention classful addressing. You need to know about classless addressing, but it's useful to get a bit of history. So how did we divide up these IP addresses historically? Well, a system of classes was used to define the network and the host part of the IP4 address. And this divided this address in a very small number of fixed ways. So this is what we used to call a Class A IP address. With a Class A IP address, the first byte identifies the network. So of course, if we only use the first byte, that's 8 bits, we can only have 128 networks. However, because we've got 3 bytes here, these 128 networks can have upwards of 16 million hosts. So of course, although we can only have 128 networks worldwide, essentially, these would only be applicable to the largest multinational government organisations. Class B networks were divided into 2 bytes and 2 bytes. Now, to identify a Class B network, by the way, the first 2 leading digits were 1 and 0. That left 14 bits for the network identifier. Now this allowed up to 16,384 Class B networks, and each host on one of those networks would have one of these IP addresses, and that allowed for up to 65,000 hosts. At the far end of the scale, we had Class C networks. A Class C network was identified by the digits 110, which left us 21 digits for the network. This allowed 2 billion networks to use this IP, but within each network you could only have 256 hosts, which is still perfectly fine, for example, for most small and medium businesses, schools and home networks. However, a much more modern method has now been used, which is called classless addressing. With classless addressing, we can split the address at any point we like. So here we've split the address on 19 bits. So the first 19 are being used for the network identifier and 13 are being used for the hosts on that network. And you can see that is how we represent the split, IP address /19. And with classless addressing, we use what's known as subnet masking along with the IP address to achieve this. So let's explain how this actually works. So here's the actual IP address shown in this blue section, and here is the subnet mask. We need to be able to pull out which part of this is the network ID, so it identifies what network we're on, and which part identifies the host, the computer on that network. So here we have a subnet mask of 255.255.244. That's because the first 19 bits are set. And what we do is we place a 1 in every location of these first 19 bits. So you can see the subnet mask has been filled with all 1s here, that's 255, all 1s here, that's 255, and 1s in the 128, 64 and 32 column, so that's 244. This subnet mask is then ANDed with the IP address using the bitewise logical operator AND. In other words, if there's a 1 in the IP address and there's a 1 in the subnet mask, we write a 1 here. If there's a 0 and a 1, then ANDing results in a 0. Effectively, what this is doing, by performing the bitewise AND operation, we are copying the IP address from here into the network ID. 1 and 1 is 1, 1 and 1 is 1, 0 and 1 is 0. So this digit gets copied here. That works up until we get to the host part. The subnet mask here is all 0, so regardless of what this is, we end up with all zeros. And this allows us now to determine which part is the network ID. When we send data, the subnet mask and the destination IP is used to work out from the network ID if the destination computer is actually on the same sub-network. It does this by performing the bitewise AND operation on the computer's own IP address and the subnet mask. If these results match, we know the computers are on the same network. If not, we now know the data has to be sent onto the router, and then that router will pick it up and send it out towards its destination. Now, often, large organisations want to further subdivide their own network into smaller subnetworks or sections. And there can be a good reason. Let's say you're a large organisation with several hundred or even thousands of computers. You may want to compartmentalise various buildings or departments. This can improve stability, speed, avoid data flying over the entire network when really it can be isolated to a single building. A subnet ID is used, but this has to come from the most significant bits of the overall host ID. This example is using the first 8 bits of the original host ID to now be a subnet ID. This has now effectively created 256 new subnetworks for the administrator to configure, with each network having a maximum of 254 hosts. That's the maximum of 256, excluding the all 0 and the all 1 addresses.